So the question I want to put under your attention at this moment and during this lesson is this one. What is scientific evidence? How can we obtain a scientific proof? So basically, I'm asking you what can be considered as science and what is pseudoscience or non-science. Obviously, science is made of scientific proofs. But how can we tell the difference between scientific proofs and other types of evidence which do not make science? So let's go through this presentation here. My question now, what is science? Clearly, we know that science is not just an intuition. It might be a brilliant intuition, but it is not science um, until we are able to prove that our intuition is right. So clearly, science is not a theory. This is a brilliant theory you see there, but it is not yet science until we can prove that it is true. So, in order to have science, we need to have scientific proofs. So, what should we rule out from science? Science is not brilliant ideas. Science is not elegant theories. Science is not faith. Science is not public opinion. Science must be something different. And so here, this is an interesting slide because I have written some statements and put them in order from pseudoscience or non-science towards science. So clearly, an untested guess is not science. A faith in something we believe is going to happen is not yet science. Deduction from previous knowledge experience, this is becoming closer to science, but it is not yet science. Science is made of objective statements which are always right, independent from the observer. This is science. And yes, this is another slide which tells you that science doesn't care about your opinion. I can have an opinion, but the fact that I have such an opinion, it might also be a strong opinion, but that doesn't make science yet. We need more to talk about science. So this is an important observation, which is attributed to the scientist Edward Deming, although he says that he has never said so. But the aphorism is this one: in God we trust. All others must bring data. So in order to make science, we need data. There is no science without data. But yet, data is not enough. Let's go through this aspect. Data are central from Galileo Galilei. So the scientific method, which was invented by Galileo, is made of asking questions, defining hypotheses, making experiments, and harvesting data. Then we use this data to reject, accept hypotheses. So data is central to the scientific process. But as I said before, data is not enough. Indeed, science is data, but data is not enough because bad experiments result in bad data. Trash in, trash out. That is what we usually say. So we need to have good experiment to have good data. What is the problem with experiments? The problem is that every experiment is subjected to a lot of sources of uncertainty, which may randomly provoke effects. So we can never be sure about our data. Basically, we have two types of uncertainty. We have the experimental error and the sampling error. The experimental error is the error we can make when we measure something. For example, here, if you look at these two plants here, they were treated exactly the same way, but this one is bigger than this one. So same treatment, different effect, because there is an intrinsic experimental error which is due to individual subject-to-subject variability. This is one component of the experimental error. More, the objects we are going to measure are not totally regular in their shape. So, for example, if you want to measure the diameter of a melon, then you make mistakes because the melon is not spherical. So, depending on where you take your diameter measurement, you can get different results. And therefore, this is another component of experimental error. We can make errors while we measure because no instrument is totally precise. And this is another component of experimental error. Then we can have intrusions. For example, here, something might happen during the experiment which provokes variability into our results, so that if we repeat the experiment, we get a different result. These are all sources of experimental errors, and we feel that these sources of errors can be minimized if we do things properly and if we avoid all types of variability. But there is another component of error which we cannot avoid, and that is the sampling error. When we make an experiment, we cannot, of course, measure all the possible subjects because there are too many and we have no money and no time enough to make a very big experiment. So we are forced into making small experiments. So we don't take the whole population, we take a sample from the whole population. So the first problem we have is that our sample must be representative. And we can do something about this. We can we can adopt a good experimental protocol by which we are almost sure that we can have a representative sample. But nonetheless, samples are all different. So if we take one sample, we can get a result. If we take another representative sample, well, we very reasonably obtain different results. So units change at every sampling effort, and there is nothing we can do about this. Every sampling effort leads to different results, and this is a source of uncertainty which we cannot avoid at all. So look at this example here. We have treated and untreated units. And if we consider the first sample, the first sampled unit, we see that treated is much higher than the untreated. But if we consider the second unit, well, the difference is small. Here it was big. And if we get another unit, and if we sample another unit, then the effect is reversed. And then again, it is reversed. So we feel that every sample we add, the results can be modified. So we are never sure what it is going to happen if we take another individual. What should it happen if we sample one more individual? So we are never sure. At some stage we have to stop, but we feel that if we go ahead with sampling, the results are going to change. And there is nothing we can do about this. So the question, what would happen if we take more data? We don't know. So if we make a soccer example, such as Spain against Italy, doing some experimental work is like trying to guess the final result when we look only at the first half of a match. This is like doing an experiment. For example, it is clear that the only way we have to know exactly the final result is to watch all the match. Otherwise, we cannot really know how the match finishes, but we can only make a reasonable guess. Such a guess must be based on what we observe. Is this clear? If we only look at the first half, then we can never know the exact final result, but we can make a reasonable guess based on what we have observed. For example, if the first half finishes 0-0, then we cannot make any reasonable guess, and this would be an inconclusive experiment. On the contrary, if we observe the first half and the final result is 2-0, 2-0, then, well, we have some loose evidence that Spain might win. But this is just loose evidence because we know by experience that a team might score 3 goals in the second half. So there is still the possibility that Italy wins. But based on what we see, we have a loose evidence that Spain might win. Well, if the first half finishes 5-0, then we have some strong evidence that Spain wins. You see? So based on what we see on the first half, we can reach a reasonable guess based on what we observe, and what we observe can be loose or strong evidence or no evidence at all. One aspect that is very important is that experiments represent the first half. The final results would be given if we sample the whole universe of possible individuals. We can't. We take a sample, so we observe only the first half of the whole match. And based on our data, we get an evidence, and the evidence is not, and not all the evidence is equally strong. So we need to be able to say whether the evidence we have is loose or strong, or if we have no evidence at all because our experiment was inconclusive. So I hope I have cleared up a little bit the problem. So let me summarize. Science needs proofs. proofs can be obtained by making experiments and collecting data. But these data must be reliable. And what is reliable data? We have at least 4 traits which we must keep into consideration to state whether our data are reliable or not. The first trait is the precision. The precision is, we could say that the precision is the number of decimal digits. So the more precise is the value we get, and the more precise is our data. But we don't consider this definition of precision. We consider a different definition, which is data is precise when, if we repeat the measurement, we approximately get the same result. So precision is related to low variability in our case. Precision is important, but accuracy is even more important. Accuracy means that our measurement is close or equal to the real value of the measure. For example, if I have a person and this person is 180 meters high, then my measurement must return approximately 180 meters, and that would be accurate. Accuracy is more important than precision, because a measure can be very precise, but if it is not accurate, then it is just trash and not useful at all. On the contrary, if a measure is accurate but not precise, well, it might not be strong evidence, but it is still valid because it is accurate. Then we have 2 other traits. Data must be replicable. Replicability means that if we repeat the measurement or the experiment in the very same conditions, we get approximately the very same results. Replicability is fundamental. Reproducibility is important, but not as fundamental as replicability. An experiment is reproducible if it gives the same results when it is repeated in different conditions. Clearly, it is not necessary that the experiment is reproducible, because it is perfectly possible that repeating the experiment in different conditions, for example, in different environmental conditions, we can get different results, but that does not undermine the validity of our experiment. So, what is important mainly is accuracy and replicability. Precision and reproducibility are important as well, but they are not fundamental to define reliable, meaning valid, data. Well, my question now is, can we get unreliable data? And the answer is, unfortunately, yes. I just wanted to show you one example of the so-called Murphy law. The Murphy law acts very importantly when we make an experiment. And if that happens, simply our data are lying to us. And this might happen very frequently. When the data
are lying to us, we say that the data are biased. So this is the expression: data are either accurate or they are biased. And we need to watch out from biased data. This is a very important and famous example. In the end of the 80s of the previous century, two American scientists, Flashman and Pons, claimed that they had reproduced the cold fusion. That was a very interesting result, because you might know about cold fusion. It's our savior from energy problems. Unfortunately, nobody has proven that it is possible to obtain it. But these two scientists did that. They proved they had reproduced cold fusion. And well, further experiment said that they were wrong. So they had obtained invalid data. So you see that it can happen that we have invalid data, even if we do not realize it. So someone has said so. If we do not know whether our data are valid or invalid, how can we have science? Here we have the key point. The key point is to apply rigorous methods so that we can be as sure as possible that the experiment is valid. So you see that the validity of data is not an intrinsic property of data. Is relating as is this assumed as the consequence of valid methods. So we have valid data because we have used valid methods. So we do not really know if our data are accurate or not. We may not know it, but if we have used the correct methods, then we can assume that they are valid. This is really a very important approach to science, because we always think that science must necessarily be the truth. We do not know whether the science is the truth or not. We only know that we have used the right method. So there is no way to put under the discussion the idea that the data are valid. I'm not sure whether I can be clear at this spot. I'm reading the final point of this slide. The scientific proof is such not because we are certain that it corresponds to the truth, but because we are certain that it was obtained by using valid methods. This is very important. So science is not necessarily truth. Science is science because we have used valid methods. That definition is a valid method. We have seen that the data are valid if the method is valid. But what is a valid method? First of all, it is important the approach we have to research. We still follow the so-called falsification principle. Maybe those of you who are in psychology know about Karl Popper. He lived at the beginning of the previous century, from 1900 to 1994. The fact is this one. Used a perfectly valid method, and we might have produced a perfectly valid scientific proof, but we can never be sure that we are right. because there could always be a future observation that says we are wrong. So this is, something which usually surprises people listening to this class. We are never sure we are right, because in the future, there might be other data that say that we are wrong. So if we cannot demonstrate that our data are true, we can demonstrate that they are false. At the moment when I find something which is against the previous theory, I have enough data to say that the theory is wrong. So I can prove that the theory is wrong, but I can never prove it is true. This is known as the falsification principle, and we strictly follow this falsification principle. Anytime we do an experiment, we do this to reject hypothesis, not to accept hypothesis. Right? So when we have an hypothesis, we can say that the hypothesis is wrong, but we can never say that it is right. This is a very important spot. Therefore, I would like to ask you whether we have questions about this. Any questions? No questions? Is that clear for you? This is something you have to remember for the whole course. We design experiments to reject hypotheses, not to demonstrate they are true. We cannot do that simply. We cannot do that. If there are no questions, I would make a further step ahead, which is the last one for today. How do we design correct experiments to reject hypotheses? This was the main topic of study of one famous scientist, an English scientist. His name is Ronald Fisher. He was born in 1890 and he died in 1962. And in 1935, he wrote a famous book titled The Design of Experiments, where he set up the three main elements of valid research. So Ronald Fisher is telling us which are the elements that permit to say that an experiment, a method, is valid. The first element is control. What do we mean by the word control? This is the first rule. We need, when we make an experiment, we need to control all stimuli, meaning all variability sources, except the one that is under study. I will show you this with an example. Look at this example. This is a field where we grew a crop by using a special innovative fertilizer. So it was not a fertilizer, it was a herbicide, but it's the same in principle. So we used such innovative herbicide and we obtained 20% yield increase with respect to usual yields. Well, you may not be expert about agriculture, but it should anyway be clear that this is not really a valid experiment. We have used the new herbicide, but there were other effects acting on our field. The climate, for example, the soil, the irrigation. Maybe we used some special cropping techniques in this year, so that we did not know which of these effects we should attribute the yield increase to. So we are not sure that the yield increase is due to the herbicide. This is clearly an invalid experiment. We have to provide control. And how do we control? We use two fields, one here and the other one here. We spray one field with the new herbicide and we leave the other field untreated. As these two fields are one close to the other, we can be reasonably sure that all other effects, the soil, the climate, cropping techniques, and whatever, everything is the same apart from the herbicide. So this is a very naive example of a comparative experiment. When we make an experiment, we need to exert control, and we control an experiment by leaving everything equal for treated and untreated subjects apart from the treatments. Right? Couple of minutes to ask you whether we have questions. Is everything clear so far about the control? Any questions? No questions? Is everything clear? Yes or no? Can I have just brief feedback so that I know that I can go ahead? You did not fall asleep. All right, that's good already. Do you think that this is enough to have a valid experiment? I mean, making a comparative experiment the way we see it in this slide, is that enough to have a valid experiment? Again, a question. Yes or no? What is the answer? Well, I'll tell you, the answer is no. This is not enough to make a valid experiment. How can you know that the effect did not occur by chance? How do we know that the effect is reproducible, better, replicable? We need to prove that the effect is replicable. And here we saw it happen just once in one field. So clearly this is not enough to prove that the effect is replicable. So we come to the second rule. The second rule is replication. And this is the rule. We need to prove that the effect is replicable by using more than one experimental unit. This would be an example. This is a replicated experiment. We did not take only 2 fields. We took 8 fields. We treated 4 fields and left untreated the other 4. So in this case, we know, we can see whether the effects is replicable, because it must happen 4 times, not just 1. So this is the second rule for valid experiments. A valid experiment must be replicated. Here I'm talking about replicability because we are working in the very same conditions, because the replicates are all grown with the same environment. We have the same soil, and we are in the same time. So the environmental conditions are the same. So we can prove that the experiment is replicable. It would be different if we made two plots in 1 year and the second replicate the year after. The second replicate would have different environmental conditions. Yes, sample size is a concept relating to how many replicates we have. Okay, so what we are replicating here is the same experiment in the same conditions. If we make a new experiment, unless we work in the greenhouse or climatic chamber or in a way that we can control everything, if we replicate an experiment in different conditions, that's another thing. Because if we cannot obtain the same results in different conditions, that does not invalidate the result. It only says that the results depend on the conditions, but it doesn't say that they are invalid. Otherwise, here, replicating the experiment in the very same conditions, if we do not obtain the same results, then the results are invalid because they are not replicable. I hope I'm clear in this subtlety. It may seem a subtlety, but it's fundamental when we have to judge whether we are science or pseudoscience, right? Other questions? So I'm going to the third rule. We have one problem with this experiment. Now, you have to think about a field experiment in this case, but we might say the same thing for all other experiments. There is one thing that we cannot be sure of here. What if the soil is more fertile on the right side than in the left side? That can happen. Every agronomist would say that the soil can be very different from one side to the other side. We can have 4 fields on the right which are more fertile than the fields on the left side. This would invalidate the experiment because we might mistaken the fertility effect with the herbicide effect. This is really wrong. It is called confounding. Confounding the treatment effect with some other intrusion, with some external effect. This is the most dangerous thing in science, confounding. And how do we avoid confounding? The only way to avoid confounding, or the only way to be sufficiently sure that we are avoiding confounding, we are never certain, as we said before, is to use the so-called randomization. We need to, that is the rule, if possible confounding effects cannot be controlled, all units must have the same chances of receiving them. Treatments need to be allocated at random. Well, if we allocate the treatments at random, it is almost impossible that we have all the 4, 5, 6 replicates of the same treatment having the same confounding effect, and the 4 replicates for the other treatment do not have this confounding effect. Because all the units have the same chances of receiving the confounding effect, and therefore the chances that all replicates for the same treatment have the same confounding effect is really minimal. It is not impossible. Yes, we know we can never be certain, but still the chance is minimal. And this is an example which is not really random, because we cannot be totally random with just 2 treatments. But you see that in this case, I have 2 plots, 2 fields treated on the left side and 2 fields treated on the right side. And so this minimizes the chances that all the 4 treated replicates are more fertile than the untreated replicates. So I'm going to the conclusions. What is science? Science is, and now we have to be clear in our definition. Science is made of controlled, replicated, and randomized experiments. Only with this type of experiments we have made a contribution to science and to scientific knowledge. All the rest is pseudoscience, no doubts. So science is made of controlled, replicated, and randomized experiment. All the rest is just pseudoscience. I'm making a very strict distinction. Perhaps I am too strict, but I need to pass certainty, at least in this respect. I have to add something, however, because we have worked, in this example, we have worked with so-called manipulative experiment. I mean, we took some fields and we allocated treatments. We cannot always allocate treatments. And for those who are working in psychology, this is maybe common sense. We cannot allocate a certain disease. We cannot necessarily allocate a certain infection, a certain pathological entity, or whatever. We can do this with plants, but we cannot do this with humans. Therefore, we can make a different type of experiments, which is called observational experiments. These type of experiments are not manipulative, but they are valid nonetheless. In this case, we do not allocate treatments. We take experimental units which are naturally treated. I mean, I go and sample individuals who have a certain pathology, who have assumed a certain risk factor. Okay, so I go there and look for these people, and I do not spread infections or whatever. These kind of observational experiments are are valid, but I would say that they are one step below the manipulative experiments because they cannot be totally controlled. When we go and sample people with a certain pathology, we have differences because we have male, female, we have people of a certain age or another age. We are people who are overweight, underweight. So there are differences, and controlling for all differences may be difficult. So in this case, with observational experiments, we must always suspect the existence of possible confounding factors. Okay, so science is made of controlled, replicated, and randomized experiments. These experiments can be done as manipulative experiments where we allocate treatment and we can control for all, or at least a main part of confounding factors. Then we can also have observational experiments where we do not manipulate the unit. We simply select treated units. In this case, our control capability is lower, and therefore we need to be more careful when drawing conclusions, right? Well, it's 1:12. Maybe we have some more minutes. I'd like to stop a little bit before today because I have another class at 2:30 and I have to go back home and eat and come back. That will be a live lesson. So I would like to stop a few minutes before, but I will give you some examples of invalid experiments. Invalid methods. Invalid methods give invalid data. Invalid methods are those where we note that there was no control or there was not a good control. Invalid methods are those where we have no replication. And be careful. When I'm talking about replication, I'm talking about the so-called true replication. For example, look at this slide here. I have two fields, one on the left side and one on the right side. So I have no replication, but then I collect one plant from this field and another plant from the same field. So I have two plants for the treated field. And here I have two plants for the untreated field. Clearly, these are not replicates. These are not true replicates. We call them pseudo replicates, right? If we have made some mistake while making the treatment on the right field, both the replicates have received such a mistake. So these are not true replicates because every possible error in the left field carries over to all the pseudo replicates taken in that field. And if we have pseudo replication, the experiment is invalid, like if we didn't have replication at all. This is very important. I will tell you something so that you can be, so that perhaps I'm clearer about the confounding. This is what happens. We have the stimulus, we have the response. The stimulus is related to an external confounder, and the response is as well related to an external confounder. So we see a correlation between the stimulus and the response, but there is no direct cause-effect relationship. It is just the external confounder which mediates the effect. An example which is usually given is this one. It's a paradox. The number of crimes in cities is highly correlated to the number of churches. This is a paradox, but it happens always. Clearly, there is no direct relationship between the number of churches and the number of crimes in a city. But both quantities depend on the number of citizens. If we have a high number of citizens, we have a high number of crimes, and we as well have a high number of churches. So we see that the number of crimes and the number of churches correlate to each other. But it's not a cause-effect relationship. The relationship is like A implies B, and A implies C, but B does not imply C, or vice versa. This is a very trivial but clear, I think, example of confounding. There is an external cause for both our observed variables. We need to be careful because if we go through the internet, we find examples of very stupid correlations, such as the correlation between the sales of sour cream and the deaths from motorbike accidents. This is taken from the net. It is not possible that if the consumption of the sour cream increases, the death from motorbike accidents increases as well. I mean, there is no relationship between the two, but they nevertheless correlate. So correlation does not mean causation. Here is the rule. Correlation does not imply causation. And this kind of correlation sometimes arises in observational experiments. So we need to be very careful about spotting it. Here we have another example taken from the internet. The number of people who drowned by falling into a swimming pool correlates with the number of films where Nicolas Cage appeared in. Stupid, isn't it? But nevertheless, these two quantities correlate. It is just a chance correlation. There is no causation in between. But we need to be careful because if we look at data where there is some confounding, we might mistaken random correlation with cause effect, which is the worst mistake we can do in research. There is a couple of slides I would like to show you, but I will do this tomorrow because I would like to take some time. I would just like to tell you that we cannot always be sure when we read some paper or some information. We should be able, in order to understand whether such an information is valid or not, we should be able to read the manuscript, go through the manuscript, inspect it, to spot possible methodological mistakes. And sometimes we cannot do that simply because we have no competence to do that. I would never be able to say whether a paper in psychology has used valid methods because I'm not an expert. I'm an expert about agriculture. So how can I trust about a scientific source? I do so because thanks to the process of peer review, which those of you who are in PhD studies, of course, know, but all the others may not. The peer review process is a process where a scientist makes a research and he wants to publish it, sends the manuscript to a journal. The editor selects a few independent experts to have the manuscript reviewed, and the expert examine thoroughly the manuscript to see whether there are strong methodological mistakes. And if there are, the manuscript is sent back to the author so that it can be corrected. Then it is resubmitted. And the process goes on until the editor is totally sure that there are no methodological mistakes. Afterwards, the paper is published. For those of us who work in the scientific field, the peer review process is something like this. This is me trying to publish my last manuscript, and then this is the route I have to follow, and I have to be able to escape all these nasty reviewers to have my paper accepted. But once it is accepted, we can all be reasonably sure that the manuscript, the paper, does not contain methodological mistake, and therefore the data is valid. Be careful. We are not certain that they are valid, but we are reasonably sure that they are valid because the methods were valid.